Can you guys hear me? Great, wonderful. So I'm recording this video at home, so you might hear some noise. I apologize for that. Let's see. Okay, so it's 5:30. Let's start. And let's say, so does everybody can see the slides, right? It's in the slides, you know. Give me a, okay, wonderful. So here's the slides. So today, that's the third time, right? The third time that we are using the Zoom to give lectures, okay? This will be the last time. Okay, let's start. So in previous lecture, we discussed what a team project is, right? So hopefully you have some idea of your own projects, right? Or you have some time to team up, right? So you still have like 4 weeks to do this. So just you know, but you need to start to think about it, right? So that's the team project. And the second part in this lecture, we talk about the recitation, right? So pretty much is about there were like 4 problems we reviewed, right? And then we completed this whole problems together, right? That's a recitation. So, and I also uploaded the solutions to these problems. So if you have some questions, or you know, you might have some questions about the coding, right, or something, just email me so that hopefully I can give you some answers. Okay, that's the previous lecture. So for today, we're gonna do just one thing, which is the one algorithm, which is called a steepest descent algorithm. You might be able to, you know, I think from somewhere you may heard about this term, right? Steepest descent. Actually, it's pretty efficient, and it's a very, I would say, a widely used algorithm. So I think like in modernized like machine learning or something like this, they're actually using this kind of algorithm. It's steepest descent. Excuse me. So for this algorithm, it's pretty much that's the very widely used. Okay, so For this algorithm, I plan to have 3 parts. The first part is give you some idea, the overall idea of this algorithm, so that you can have a sense of it. And then we can have a formal development of this algorithm. And lastly, I will show you, or in the Matlab, how to implement this. Okay, so let's come to the idea, right? So what is the idea, the key idea of this algorithm, the steepest descent, right? So here actually there is some like metaphor, or there's a kind of a, suppose there's a kind of a problem like this. It's in this slide there is a kind of a hill, right? So it's kind of a mountain. So I don't know how how do you think of it, but actually it is a 3D. It's a kind of 3D surface, right? Is it 3D from your side? So anyway, that's kind of a 3D graph. So hopefully, so for each curve, that will be the contour, right? It's kind of the height of it. And here's the problem, right? Suppose there's a here, or here pretty much is a function, right? Imagine that you are kind of a climber or something like this, right? You are walking down here in a very foggy mountain. So the problem is that this is a mountain, right? But it's very, very foggy. So which means you cannot see very far away. You can only see like a very, very short distance. Okay, that's a setting. So, and the thing is that you are kind of walking down here. So you want to walk down, and you want to for example, you want to achieve reach the bottom, as soon as possible, right? Because it's kind of getting late, right? So you want to walk to the bottom as soon as possible. So what is your strategy so that you can get the bottom quickly? So let's think about it. So what kind of things you want to do? So you are kind of walking in a very foggy mountain, right? But you want to kind of get down, right, to the very bottom quickly. So what would be your strategies? Just give a discussion. Anyone can have idea how to really get down. Yeah, I think that would be a very good idea. Yeah. Yes, I think that's a very good idea. So you can use it. Yeah. So I think that would be our methods. Exactly. We're trying to I think, yeah, we're trying to do something similar. So we have a ball or a kind of things, right? We just roll it, or you can roll yourself, right? You can kind of form yourself like a circle or a kind of ball, and then you can roll yourself. But the point is that I think you get some idea, right? You want to use a ball why you want to use a ball? I think, yeah, some Yuri says that you want to take a ball and see where it goes, right? So the idea is that the ball will pretty much, kind of find the very steepest, direction, right? That's something you want to follow, right? I think that's the key idea, right? Because, because you cannot see very far away. So the only kind of a strategy or decision you can do is that what is the steepest direction at current position, right? Suppose that's, you can see that the climber is, pretty much is something like this, right? I think that's the key idea of this steepest descent, is just to find the kind of direction to follow, right? So here, of course, I show up a one direction, right? This is definitely the worst case, right? It's kind of uphill, right? So you don't want climb, you don't want climb up, right? You want to kind of walk downwards, right? So that's something, this is a worst case. But this is a very important idea. It's called uphill or gradient. So the idea is that if imagine that you are kind of sit in that kind of a contour, or you are kind of on this mountain, right? So if you turn around, and you can see that if you face the mountain, right, that is uphill, right? That gives you the maximum kind of a lift if you walk along this direction, right? Which is very bad for us, right? We don't want to climb up, we want to walk down. So there are some other options, so which is kind of they are shown here. So the red, if you can see the red, right? This is called downhill direction. So which is also the direction if you put a ball in that kind of location, it will you're kind of falling from along that direction, correct? So that would be the a good way, right? So the idea is that you can really you want to follow the red direction, so which is called downhill direction. Actually, this red, if you take carefully look, if you take a careful look, you can see that the red one actually is in the opposite direction of the uphill, right? So actually this is kind of negative or the opposite of a gradient direction, right? Because gradient, which is the black direction, will give you the maximum lift up, right? But the red one actually will make you like, kind of a decrease. That's, very efficient. Pretty much that's the very two extreme situation, right? And besides these two extreme situation, there are two, kind of a two direction, right? Which is in the color of cyan, right? If you can see, take a look, that's very light kind of a color. So for that two directions, actually, they are called zero slope direction, right? So you can imagine that if you walk along this kind of, these two directions, so pretty much there's no height change, right? You are kind of walking in a very flat kind of a road, right? Very flat trail. So that's something we don't want, right? We want to have a very kind of a, dramatic change of the height, right? So that's the red direction we give us. So that's something we could say that that's something that we are kind of inspired from the ball, right? So because the ball will falling, will fall through this kind of red direction. So that's something we want to follow, right? And here's something very different from the boy's next step. So let's say, okay, we have determined that we will pick the downhill direction, okay, which is the red direction. Okay, that's will be the direction we want to follow. And then a further question for us is, how far should we walk along that direction, right? So we know that when we do the ball experiments, right, when we throw a ball there, we know that that's the direction we want to go, right? But for how long? Any idea for how long? So any kind of suggestions? So you think how far away should we go? So definitely we don't want to move very tiny medium way, right? If we kind of just walk like 1 inch or 2 inch, that's the ball stops. Okay, that would be let's say, yeah, I don't know actually. Can you catch it? Because the ball can roll very fast. I don't know but that's give you some idea, right? Some kind of a stops, right? There must be some point that would be the best, right? Either the ball stops or somewhere, right? But here is that in this setting, in our setting is that if we pick a direction of that direction, we will not change for now. We will not change it. This is different from a ball because if you throw a ball on the mountain, right? So the ball will actually, kind of, changing its directions, right? Because it can always find the best directions. But here, our setting is after we pick or after we determine the direction, so we will along these directions for a very long time. So we will not change the direction for now. So the idea is that after we pick the direction, okay, we just follow this direction and then move it to a very far away until some distance, okay? So that's very different from the ball kind of rolling, okay? So if you look at this kind of a graph, that's something, right? I rotate the 3D model a little bit, I rotate it a little bit. Hopefully you can, process them as the same, actually it's the same function, right? They are the same mountain. Here, if you can see my cursor is here. So this kind of a guy, right? It will follow this direction. This direction will not change. It will always follow that direction. But the only thing is that, so here's a decision you have to make if you want to walk through that direction, right? You don't want to walk very little, right? You want to walk somehow very far away, but you don't want to walk too far away. For example, if you follow this direction, at some point, for example, at this point, if you continue moving, then actually you are climbing again, right? So that's something we don't want. So pretty much is that we want to follow this direction, but to this point, we want to stop, because if we continue to move, then our kind of height will increase. That's not good, right? So this position, that would be the best position along this direction, okay? That's the idea of how far away should we walk along, right? So the essential idea is that we will keep that direction. We don't change it. We just keep that direction and move it until some point that give us the best position, right? Correct? So that would be the idea we want to walk, actually. So this is somehow different from the ball, right? Because the ball can always change its direction. But for us, once we determine that we will go to the north or we'll go to the north-south, right? We will permanently following that direction until we reach the best position in that direction, okay? That will be our setting. And then until this point, right, what we will do next is that we'll repeat the previous two steps, right? We first, maybe at here, we will use a bar here to redo the direction evaluation, right? So at here, we may just throw the ball again so that to try to find another, kind of a gradient or another downhill direction. And then we will move, right? We will move along that direction to some point, right? And then, so probably, kind of repeat this for many iterations, and then finally you will get the idea, okay? So probably I can show you a kind of a animation or Matlab so that you can have a better idea. So let me just do that. How about just give me 1 second. I will just do the, kind of, simulate the process I just mentioned, okay? Just give you some idea. Okay, let me show you how to do that. Give me 1 second. Just 1 second, okay? Just 1 second. Let's see. Okay. Probably let's say what is that? This guy possibly. Can you see figure 2? Oh, it's already done. So can you guys see the figure 2? Okay. So let me see. Actually, this is how the kind of things. Let me just move this away, right? Just move this guys away, and you can see that. Hopefully, you can see a 3D. I'm rotating this function. Can you see that? I'm rotating this kind of a function. Great. So if you can see that, hopefully you can recognize this guy as a 3D thing, right? It's a kind of a here, right? So initially we are here. So if you can see my cursor, right? Here. And then at the first iteration, you will follow this kind of, the direction, okay? Follow this direction. And then until some point here, this is the red, a kind of star point. That will be your, the best location along this direction, right? Because if you move forward, if you continue to move along this direction, then the height will increase, which is not good. So we will stop at this kind of a best location at this, along this direction, right? And then we can reevaluate the direction, and then which is pointing down along this kind of thing, right? And then we can do this, right? So let's see if we can, how about this, right? Let me just, can you see that? That's 2D contour, right? That's in a 2D contour graph, correct? You see the 2D things? Okay, wonderful. So if you see the 2D things, you can see here, let's, to the very, probably let me just rerun the code, then hopefully you can have a better idea, okay? So let me see. Just 1 second. Probably let me just give me 1 second to, yeah, just 1 second. Let me rerun this code. Hopefully you can have a better idea. Okay, I give you figure 3. Figure 3. Okay, so in figure 3, that will be the initial state. There's nothing there, right? And if you look at carefully, you can see that, because in my cursor here, right? There's a red spot. Can you see the red spot? Okay, that's great. So that will be our initial guess, right? We guess that that will be somewhere here as 1.5 and the y is 0.5. So that will be our the first initial guess. And then, so at that point, we can run one iteration, right? We can do something like this. So pretty much is, see that? So the idea is that we know that this black, that will be our direction, right? If you look at from very top, that will be our 2D contour, right? From 2D contour, you can see that this is a straight direction, right? So pretty much we are following this direction. We don't change it. This is very different from the ball, right? Because for the ball, if you roll it, it will actually change the directions all the way. But here, for us, for this kind of algorithm, it just keep that directions. When you pick that direction, you will kind of temporarily fix that direction and then move until this point. You find that will be the best along this direction. Because if you move far away, for example, move to here, then the height will increase. And also, if you don't move to here, somewhere in the middle, then it's also not the best. So I can actually, for example, I can rotate a little bit. You can see that. So actually, it's a curve, right? This is a kind of you are moving from this point and along that surface and mountain and gradually down here to here, right? That will be our one iteration. So you just initially pick one direction and then move some distance. Right? It's like shooting. I got it. Oh yeah, that's a very good idea. Yes. So that's something like yes, like shooting. Yeah, just go along that way. I think that's a very good point. So you will not change the direction, or you can think that yeah, that's the way to do it, like shooting, or is that shooting? Anyway, but you can imagine there's a plane or something like this. But in central idea is that in 2D, so that's why I think 2D is better. So in 2D, actually, this is XY, right? That's in XY position. That will be a straight line if you want to think it like this, okay? So that will be our first iteration. And then let me run the second iteration for you, okay? So let's say in the second iteration, just 1 second, let me run it. So you can see that, right? So it's like there's another direction, right? Because when you reach, or when you kind of reach this point, right? That will be our new starting point, right? We need to reevaluate the direction, correct? And then it will repeat the previous process, right? And then at this end, that will be the best along this direction, okay? And let's take a look at the kind of 3D. If you look at 3D, that would be something like this. And hopefully from 3D version, from this kind of 3D view, you can agree with me that this kind of, at least for this direction, right? This point, that would be the best along this direction, correct? And then for the second direction, so from here to here, this end will be the best point, okay? So that's something, that's the essential idea of this algorithm, right? So essential idea is that you will pick one direction. That direction is the best for this kind of position. You just pick that direction, and then you move along that direction to a point that will give you a best result, right? That will be the one iteration. So you can imagine that pretty much that's just 2 steps, right? We just find the direction and then determine where to start and then repeat that process. So clear about this idea, everybody? Okay, that's wonderful. So let's come back to the wonderful. Thank you. Trust me, it's not Corona. So let me just redo let's come back to the slide. Okay, so this is a slide, right? We just demo the kind of a curve, right? So now let's develop, use some formal way to develop this algorithm. So as I told you, right, as we mentioned, for each iteration, we have 2 steps. So step 1 is to find the downhill direction or the steepest descent direction, right? That will be the step 1. And step 2 is to determine what is the distance should we move, right? So what is the best position should we move? Or that's a second step. So essentially that's 2 steps. So let's try to find the first step, how to find the downhill direction. So as mentioned before, the downhill direction is actually the opposite of the gradient or the uphill, right? So the reason we want to show uphill, because for uphill direction, that's something like it's naturally equal to the gradient direction. So for gradient, if you know from calculus, actually gradient has the del f. So this is a kind of a mathematic kind of a formula, right? The gradient is equal to the partial derivative, from the function, our function with respect to all the variables, right? For example, in our case, this is a kind of a 2 variable problem, right? We have x, y as the parameters or as the variables, right? And then, so for this kind of a 2 variable problem, so we have the gradient as something like this, the partial f over partial x, and this is a partial f over partial y, right? That would be it's a vector actually, you can see that, because it has 2 kind of variables. So that's why we have 2 components in this kind of a gradient vector, right? So let's do a kind of practice, right? Exercise. So given this kind of function, right? So what is the gradient? So yeah, it's exercise time. Just try. What is the gradient of this function with respect to x and y? Everybody, please just give a try. Okay, I got 1 answer. Yes, another one. They are pretty identical. Same. Yeah, agree with it. Wonderful, right? So that's pretty good. So actually, yes, that's my answer. So it's very easy, right? When you computing this kind of partial f or partial x, you just regard the y as a constant, right? Then you can do something like this. So that's pretty straightforward. So I hope everybody can, generate something like this, right? If you cannot redo this, that's fine, because later, at the end of this lecture, I will show you how to use Matlab to do this, okay? So Matlab actually can help us to find this kind of a symbolic derivative or, kind of something like this. So that's fine. If you cannot remember it, that's fine. We can use Matlab to do this. But anyway, so that will be our gradient, right? We can, once the objective function is given, then we can easily compute all the gradients for a specific point x, y, right? So that's the idea of the gradient. So then come to our step 1, downhill, right? Or steepest descent direction. So as we mentioned before, so the downhill, that will be the opposite of gradient, right? So the opposite will be the lective of this one. So that's pretty simple, right? So S will be our downhill direction. The S is also for search, so it means the search direction. Okay, so that's why I put S here. It means our search direction, which is equal to the negative of gradient, right? So every component will have a negative or kind of minus here. So because the gradient, the del F has two components, right? Then our S will be pretty much is a vector of two components. Okay, that's the search direction. So again, for this kind of a function, so we can simply put a kind of elective or minus before each component, right? Then we can compute the search direction. Okay, wonderful, right? So step one is done. So we just compute the gradient and put a elective beforehand, right? So that will be our step one, try to find the down here direction. Then comes out to our step two. Again, this is a oh, before that, let me show you one thing is that I already showed you, right? So this is a S is something like in 3D it's a line, right? But in 2D, if you take a look at that, it's kind of a 2D. Just show you what is the direction. If you see that here, if you see a 2D, actually in 2D, this is just a vector, right? So it's from here pointing to this direction, right? So that will be our kind of a search direction, okay? So because our design space is 2D, so naturally that would be a kind of a direct or vector of two variables, right? So just show you, so that's another reason I like the contour in 2D, because in 2D you can see that the search direction is actually a straight line, other than in the 3D that would be a curve. Okay, that's something just to realize the search direction. So it's really a direction, it's not a curve, okay? Then let's come to the second step. So the second step is trying to determine, so how far away or how far should we walk, right? So the essential idea is, as I mentioned, is that we walk until the best position along that direction, correct? So for example, in this graph, in the left graph, right, we start from this kind of initial point, and then we follow that direction until some position, right, which is here, then we can stop. So here's the question: how do you represent that all the points along this direction, right? How do you represent that kind of things? Any idea? So we know that this starting point is x star, y star, okay? The starting point here is x star, y star. By the way, everybody can see my cursor, right? The mouse is moving, right? Can you see that? Okay, wonderful. Then we are on the same page. So look at my the cursor's position. You can see that this is the starting point, which is x star, y star. And then we also know the direction, right? Which is S1, S2, right? That's a vector. So here's something like, kind of a practice for you. So given a point, x star, y star, and a kind of a direction, S1, S2. So how do you represent all the points along this direction? Give a mathematical, kind of things. Any idea? So linear function, that would be very good, yes? So more specifically, any other idea? A vector, yes. It's something like a vector, the starting point plus the direction vector times something d, right? If you use a vector, something like this, correct? Correct? Something like this, right? D will be the parameter, right? So it's kind of a parametric expression, correct? Wonderful, everybody agrees. Okay, so that will be something like this, right? So we have x star, y star as the initial points, right? And then S1, S2 will be the vector. Then we have a parameter, which is d, right? That will be the distance, right? So which is d, the distance in xy plane, right? So that will be all the points along this direction can be, formulated as this, right? So that would be our kind of, the key things here, right? So the only, everything is known to us. the x star, y star is the starting point. The S1 and S of 2 is the search direction, which is also computed, right? So the only unknown is this D, right? That's the D. And also we see that this is a point along the direction, and we want to find the best along this direction, right? So this actually is another optimization problem, right? So the best point would be the ones that minimize this function, right? If we put this kind of all the points in the direction and we plug into the function, right? That will be a new kind of, a new function, right? The only unknown variable is D, correct? And then we need to find the best D that can minimize this function, correct? Everybody is kind of, understand this point, right? So we are trying to, the problem is trying to find the best position, right? And then if we want to accurately, express this problem, is that we first formulate our points along that direction as this kind of a formula, right? X star plus D and times S, right? That will be the points. And then we plug all the points to evaluate all the points here, right? That would be the 1D problem. And then, so here is something like a more formal way to say this. So our best distance, so D best will be the best distance, right? So the best distance will be the minimizer of this function, correct? Because we see that. Everybody agrees? Okay, wonderful. So that would be, because we say that the only unknown value is a D, right? What's the distance should we move? And then if we plug into the function, the only unknown thing is that this kind of D. And then we can use 1D search, so to kind of find this D best. So what is the 1D algorithms? We already know. Give me some, names. What's the algorithms that we can solve this kind of 1D problem? How to solve this 1D problem? No idea? Just guess. So, you cannot really have a, yes, so that would be, so guess is not good. I mean, you may have something like very far away from the best. So yes, I think binary search or quadratic fitting, that would be our methods, or any 1D search. So I think, yeah, Matlab is pretty much a, that's something we learned, right? We know how to solve one variable minimization problem, right? This is a one variable minimization problem. So we can use binary search, quadratic approximation, or just use like F-mean search. That's great. So I would say yes, and plus the F-mean search, right? So that would be the easiest way. So probably in today's homework, so we will combine your first binary search in here. So we'll use binary search. So argument. So yeah, thank you for mentioning that. So here, so if you don't look at the ARG, right, that would be a minimization problem, right? And the ARG means argument, means what's the kind of parameters that really minimize this problem, right? Okay, that means it's kind of a formal way to represent the solution, okay, that really minimize this kind of things, okay? That's called argument, okay? Clear now? Okay, that's wonderful. So it means, this pretty much means like the solutions to this problem, okay? So I should mention this. Then that will be, okay, after we figure out the D best, right? Then pretty much our job is done. We just have one final updates, right? Because we know the D best, then we can use the D best, pretty much is that this is the point, right? We want to update, right? So our previous X star is kind of updated as X star plus the D best, which is this point, okay? So that will be our new best solution, okay? So by doing so, we complete the step 2 and also complete one iteration. And then we can repeat step 1, step 2, and then we can actually find a very good solutions after several iterations. Okay, so here's a kind of a summation or summary for this algorithm. So we need to do a lot of iteration. So for each iteration, we want have 2 steps. Step 1 is trying to figure out the steepest descent direction, right? Which is called downhill direction or steepest descent. Okay, that's the direction we want to figure out. And also the mathematical equation is the search direction is elective of gradient, right? The del F. And then step 2 is to determine what is distance should we move along that direction, right? So that would be the best, right? Just to minimize 1D problem, right? Along this kind of direction. So what's the best distance we want to solve? So that would be the 1D. And then we can update the X star and then repeat this process, okay? So on the bottom right, this figure, the right figure, you can see that somehow it has 7 iterations. So each black line or black segment is a one direction, right? It's one direction, second iteration, and third, there are 7 of them. I should mention one thing. If you look carefully, you can see that so each direction, each search direction is perpendicular to the previous one, right? So there are some reason for this. You can think about it why. You can think about it why. So we will cover this for next lecture. So we will discuss why we have the 2, kind of labeling directions. They are perpendicular to each other. Okay, there are some kind of 90 degrees, right? Among the kind of every direction is kind of a zigzagging, right? So that's the property of this kind of algorithm. Okay. So we are discuss these kind of things for next lecture. By definition of the gradient, yes, actually that is very true. But you need to elaborate on a little somehow, yeah, give something. That's very true because by definition, gradient is somehow, probably we can like have a little discussion. So yeah, so anyone can add small comments on this. Why these kind of 2 directions, they are perpendicular to each other. I think you already give a good point that by definition of gradient, right? Or how about this? So let's let me see. Let me just have a better view for have a bigger view for it. Let's see. Everybody can see the figure 3, right? So here. Let's use this kind of thing to explain. I think that's much better. So here, okay, wonderful. So you can take a look. There are 2 successive directions, right? So for the first direction and second direction, they are kind of perpendicular to each other. There are reasons for it. For example, so we need to utilize the contour to explain this. So first of all, if you look at this, the direction, for example, for the first direction, it is perpendicular to the contour, correct? That's because this is because of the gradient definition, because it somehow you want the maximum. Yeah, of course, that's correct. So that's because this direction is perpendicular to this one, right? The contour. That's the definition of gradient. But to this point, we still focus on the first direction. We still focus on the first direction. If you look at the first direction here, so for this kind of thing, at this point, the contour at this point is somehow parallel to, or kind of a tangent to this kind of search direction, correct? It's kind of parallel or tangent. So that's this kind of search direction. So if we have a very if we draw a contour, passing through this kind of solution, right? Then we can see that this contour is actually, at this point, is kind of a tangent. I would say the vector of this guy is a tangent of this kind of contour, okay? Here's the reason. Because if not, then we can actually move far away, right? We can cross some contour so that we can get a better solution. Only in the case that if this kind of point has the this kind of a moving direction is a tangent of a contour, then that would be the best position. Everybody agree with this kind of a statement? I mean, only when the search direction is tangent to a contour, then that would be the best position, okay? So again, so at this point, this guy is a kind of the tangent to it, right? But this guy, the second direction will be perpendicular to that kind of things. So you can see that the relationship, right? Because one thing is parallel to the contour, one thing is perpendicular to the contour, right? Or specifically, the first direction is parallel to the contour at this point, and the second such direction is perpendicular to the contour at this point. Correct? This is not related to divergence. No, I don't think so. Yeah, let me say divergence, or that's a very advanced topic. I would say my intuitive answer is no, but I may check with that. I don't think so, but I need to double check. Okay, but the essential idea is if you look at the contour, that would be my explanation. This guy is parallel to the contour. This guy is perpendicular to it. Okay. Everybody agree with me? Okay, then good. So I think at least somebody, right? Someone agree with me. Then wonderful. So let's get back to our slides. Okay, that's some properties we want to talk about. So because for next lecture, we will introduce another algorithm, which is trying to improve this kind of algorithm. Because you can say there's one downside of this algorithm is that they will zigzag a lot, right? For some functions. So that's someone are trying to improve this one. But we can talk about that later. So for today, we just talk about the very native one, right? Just two steps. One is to find the direction. Second is to find the distance. Okay. And then, so that would be the kind of the development for this algorithm. That's all for today, actually. Not all for today, but all for the algorithm. So essentially, just two steps for each iteration. Okay. So hopefully you get that key idea of it. And then here's something like some generalization for this algorithm. So because in our slides, we only use the 2D or two variable problems, right, to demonstrate this algorithm. But actually, these methods can be generalized to solve many multiple variables that with more than two variables. For example, if we have problems have x, y, z, three variables, then we can easily extend this kind of algorithm just by modify the gradient and then modify the 1D problem, right? Just add some components. So that's easy. So that's something we can easily generalize it. So that will also be your homework, right? Try to generalize this kind of 2D problems. Okay. So everybody get a sense of this, how to generalize to 3D, right? Because if you compare the 2D, this is 2D one, right? The first step is we have a gradient, which has two components. Okay. And then for the second step is trying to minimize a 1D problem, right? So which is along that direction. So the same idea is that for a 3-variable problem, you can see that we only need to generalize, or we need to just replace the gradient with a 3-component vector, right? And also for the, because naturally the function has 3 inputs, right? We have to give 3 inputs to it. So that would be the generalization. Okay. Then here comes our final, the demo things, right? So actually, I already demoed to you, but here I want to dive in details about this kind of algorithm. Okay, so pretty much that as promised, right? So we will do the the first thing is that how to use the Matlab to find the gradient, right? So that will be the first, and then I will demonstrate the algorithm. So let's come back to the. Let me just share the Matlab screen with you. So here's my Matlab screen. Okay, if you take a look at here, I'm doing the homework, right? So let me just do this. Let me just reorganize my screen because it looks very. Let me just clear the screen. And here, let's do the symbolic first. So this is a code to generate the gradient. So first of all, you want to do is here, you want to declare that x and y, they are symbols, which means they are kind of x, y, they're symbols, they're variables, right? And then you can have a kind of by doing so, see this, probably you can, this is a function, right? This is a function. So this is a function for, this is a function that generated here in the slides. Actually, that's the function I use. Okay, so pretty much is that this z equals this guy, and at this point, actually, if you want to know what is x and y, you can see that whose means like what is x and y, right? Who is this? Right? For x, y, they are kind of symbolic. And for z, actually, it is also a symbolic symbol, I would say. It's a symbol, okay? So, and then here comes the command. So you can say gradient, okay, gradient. So if you don't know what is gradient, so let's help this guy. So we can find what is gradient. So here, so you can take a look at the gradient, approximate gradient. But actually, gradient can also return the analytical one. So it's not really correct. But anyway, let's say gradient, and z will be our function, right? Because z is a kind of a symbol. It has a function. And then we can, with respect to x and y, right? So that's it. We can return. See that? So this is a symbolic computing actually. So given a, if you put z again here, z is pretty much something like this, right? As a function like this, it's pretty much symbolic, right? And then you can easily find the gradient of it. And what you need to do is pretty much is just, kind of select this kind of thing, right? And then Control C or right click, copy it, right? Copy it. And then at this point, so let's say you can copy it here, right? Let's say that would be our gradient. You can easily copy it here, and that would be our formula, right? You don't need to really type the equation here. So let's say that would be our something like this, okay? So let's say probably, let me see, gradient, for example, 1, right? Something like this. So before I can really utilize it, let me say x equals to 1.5 and y equals to 0.5, right? And then I can, because I already assigned some value to xy, then if I run the 3 kind of commands, right, it will give me the gradient one. Let me see if I copy here and then enter. I put enter here. There's something something wrong with it. What happened? Probably I need to put it here. Okay, then I think it's good. Let me redo this. Okay, I can clear everything so that just make sure everything's okay. So see that because this kind of expression I didn't really type, right? I just copied from the output of the gradient, right? So of course you can derive the gradient by yourself, but for me I think this is the easiest way, right? You just use Matlab to derive the gradient for you, and here this x and y, they should be assigned first, and then you can use it to compute, right? Let's say if I put an enter, then you can say x, y, they are assigned, and let's say if I put this guy, you can see that the gradient has been computed. Okay, so that's how we use the symbolic function. So essential idea is that you need to firstly define the symbolic xy and define your function, and then probably don't need this one. So use this command. This command actually can output this kind of expression, and then you just copy it to your code. So that's easy. Okay. Any questions about this? So there will be a homework. Okay, good. So trying to, I will give you some functions. So that's very hard for you to use your, you can derive, but maybe it's very hard to do it manually. So I hope that you can really use the Matlab symbolic to derive the function, okay? So that will be the first demo. And the second demo will be the algorithm itself. So for the algorithm itself, that will be this guy. Let's say probably I just go through it, okay? And then I don't need to write it down, right? So let's just go through, let me just go through this guy, okay? So I just go through this kind of a code, 9 by 9, right? So let's say, let's add a breakpoint at this guy, right? Then we can do debugging, right? So let's say let's run here. So if I click the run, right? So then at the first, then here there's a step. So we can click step, and then we can hover our mouse to here. So for here you can see that that will be our it says that object function is kind of a function handle there, right? And this kind of things. So that's what we want. And then here it's pretty much this chunk of code is trying to plot the kind of generate the 3D plot. Okay, so I just skip to here. Let me just run through to this guy. Okay, and then let me show you the result. So which is figure 4. Here, this is a result. Okay, so you can see that it's kind of a 2D contour, right? But here there's a rotate 3D. So if you click it, and then you can, you need to key down the control keyword, right? And then you can rotate or something like this, right? You can really have a nice view of it. So I hope that everybody really do this. Just run my code and just take a careful look at the figure or the 3D things. You will have a much better idea of this algorithm, hopefully, okay? Because this is kind of a 3D vision, so that you can really see where the algorithm really, what the algorithm really is, right? So I hope that you can take a look. So this will be the kind of the surface and the contour. And also, if you look at, if I rotate this kind of back to this position, right, that will be our 2D. So for now, I hope that you can have a connection between the 2D contour and the 3D one, right? So essentially is that each contour is actually if you look at it from this kind of side view, you can see each contour is just with the same height, right? That's just the meaning of the contour, right? Hopefully from this kind of view, you can connect the 2D contour with the 3D kind of things, okay? So you can imagine this one, right? So next time when you look at the contour, you can think about this is actually a 3D, right? Okay, that will be our first demo. Let's come back to our major code, major IDE, right? So then again, you can, if I hope that you can really take a look at this code, right? Try to understand what's the code, what are this each code is doing, right? I will add some a kind of a comments on, so that to help you understand this one. So really, I think by looking at this guy, you can have some examples how to visualize them, right? So so that's something I do. And then let's say before that, right here, that if you see here, I actually this chunk of codes, they are kind of doing initialization work. For example, we need to initialize, or we need to pick the starting point, right, which is x star, y star, and also have a y some value, and a plot this kind of things on it. And that's it. So the essentially that this chunk of code is trying to assign or trying to pick the initial point, right? And also giving some and plot this kind of points, right? So let's say if I look at the kind of a code, right? So here, hopefully you can see some, yeah, here, this is the legend. So pretty much it show you which one is which one, right? The red circle, which is here, that is the initial guess, correct? So that's our initial guess for this kind of problem, okay? So that's the first guess. And then let's come back to the major code. So we from now on, we can do the iterations because we already initialize our, we already pick our starting point, right, x star, y star. Then we can do iterations. So the first one, this chunk of code, right, is actually trying to do the gradient. So if you look at here, so the idea is that because the reason, if you look at here, why I put a new x, instead of x star, because in our symbolic code, right, I only use x and y. So I don't want to, for every x, I don't want to put an x star here. So that's the reason I use x, to kind of copy the value of x star, and y to copy the value of y star, and then put it here. Then without change this kind of expression, I can easily, compute the gradient, right? So which is this value. So if you take a look, that will be also a vector of two components, okay? And then as mentioned in our slides, right, the search direction, this step is doing a search direction. It's pretty much the negative of the gradient, right? So that give us this is a uphill direction. And then if we put a minus or a kind of negative beforehand, then we convert that guy into a kind of a downhill, right? Or the steepest descent direction, okay? And after that, come back to our, I think, second step, right? Which is doing the 1D search. Is trying to find the best D or best solution, right? Or the best position. If you look at here, so actually this is something like we utilize the F-mean search, right? F-mean search to minimize the 1D problem, which is defined in our slides, right? So because in our slides, we see that in this function, the only one unknown variable is D, right? And this is all the points along that search direction, right? So that will be our definition for that 1D problem, right? Pretty much this is trying to minimize the best location. And also we put a 0 as an initial search, right? That's the initial guess for this 1D problem, okay? And then if we, so that's simple. So we just use one line to solve this 1D search. And then if we step, right? If we run this code, it will give us this kind of value. So the D distance will be 98, something like this. Okay, that will be the distance. And then, so for the sake of plotting, so I need to kind of store, or we need to keep record for the previous star, right? This is our previous solution. So we use old to save that kind of previous initial guess, and then the x star is updated as, right? So the previous x star plus the the searching direction, right? We have the best kind of location. So that will be the updating of the stars, right? Then if we, let me see, if we run it, so you can see that X star, just changes, right, to some Y star, and Y star O is the initial guess, right, 0.5, and then update it to this guy. And also for X star, initially it's initialized as 1.5, and then we update it as this, right? So for this chunk of code is actually trying to plot this kind of a search directions, right? So that, let me just go through it. So also you can take a detailed look at this guy. So see how I really plot the kind of curve things, right, on the surface. You can take a careful look. So let me just run through this chunk code, and let me show you the result. Just 1 second, that should be figure 4. So that's it, right? So we pretty much add the solution of this iteration, right? The updated X star and Y star. And also we plot all the points along this direction, right? Which is a black, okay? So that will be our search direction, or all the points along this direction, okay? So that will be our first kind of iteration, okay? And then I hopefully everybody can read it. When when this session ends, you can run this code and trying to say, for example, here you can see that this kind of this point is actually, if you have a contour along this guy, you can see that this search direction is kind of parallel to the contour, okay? So that would be some something you can really get a sense of it, okay? Okay, let's come back to the code, and then let's just run multiple iterations. Let me see. Possibly, yeah, I still share this kind of results screen with you, but in the background, I will continue to run this code so that you can see how the plot is updating. Okay, let me just run it. So hopefully, so for every 4 seconds, so there will be 1 iteration. Okay, so you guys can see that updating, right? So right, so hopefully you enjoy this kind of animation, right? It's because something like give you some idea what is the steepest decent direction really looks. Okay, so I think that would be all for the demo. So any questions for this kind of things? So I will upload this kind of a code so you guys can really download and take a look at it. Okay, really just kind of for me it's a lot of fun to trying to watch this kind of things. Okay, any other questions regarding this kind of algorithm? No? So, okay, I think we have 10 more minutes. Okay, wonderful. So we have 10 more minutes. Yeah, maybe, yeah, I would say I have graded the homework too. So I am, I would say, extremely happy about the results. So because I think like most of you really, let's say, following the format, and most of you got like 10 points. So that would be a really good kind of, yeah, it's really good, I think. So I'm happy about it. So just keep, it's I'm not mean to give more points, but the point is that I hope that everybody can really understand it, and I think it's a very good signal that everybody is kind of understand the problem and get a correct answer. So I would say homework 2 is it's really good. Yeah, I would say you guys have a wonderful performance. So today I will upload. I haven't uploaded the solutions. I will do today or tomorrow morning, and also I will upload the solutions to the homework 3, and also the problems of homework 4. Okay, so that would be the kind of a plan for it. So probably, yeah, that will be the end for this session. Uh, so I would say enjoy your weekend. Okay, cool. Okay, wonderful, everybody. So yes, so yeah, take a look and email me any questions you may have for the coding or for the homework. Okay, so see you. Bye-bye. Bye.